Okay, so hello everyone. I'm Max from Western University, Canada, and I've currently started my PhD there. It's 9 months now, and my supervisor is Professor Peter Brown. And basically, what we're going to try to do here in 3 years, basically, for 3 years of my life, I'm trying to create a Monte Carlo model to calibrate, that is calibrated on Earth in order to define the meteoroid's environmental influence on different planets. So hopefully by the end of this presentation, you probably understand what I'm going to do for all these years. But overall, what I'm trying to kind of delve deep into are sporadic meteoroids. So these are the actual things that we're going to try to replicate this way. Then I'll kind of talk about the meteor-atmosphere interaction in a way that are present on our planet and on different planets, and the different way we can model them. There are just good way to model them and bad one. Well, more on that later. And at the end, I'm going to wrap it up with the Monte Carlo simulations. So, first thing first, basically, meteoroids are, the vast majority are basically sporadic in a sense. So they are not part of any meteor string. These one are no more than tiny pebble size objects. In general, roughly from 1 millimeter to centimeter size objects are usually the one that you can see in a normal night sky. And overall are the actual one that we want to focus on. So basically Earth rolling around the sun, moving this way, basically picks up all this material that actually happened to be on its way. And this way lead to this sort of meteors that we see on our night sky. These one are in general in the anti-helium region, you see here. And these one are the actual one that Earth is actually mass dominated by. So these are the vast majority of the sporadic sources that we see and are actually part of the vast majority of the mass that we receive are from the anti-helium sources. And here is an exemplary sort of orbit that we could see in the night sky. And ideally, these one are basically, the vast majority are from Jupiter family planetary orbits. And the rest are basically from asteroidal orbits. As you can see here, the one that we are actually trying to focus on are very, very slow in a sense. So what are we going to try to model? Are sporadic meteors with a velocity that is slower than 20 kilometers a second. These one are in general the vast majority of the things that we can see in our inner solar system. So the zodiacal cloud model actually shows that the meteor environment is not that different in our close neighbors. So Mars and probably Venus will have similar sporadic meteors. And in a way, we can try and model first, of course, the Earth, which actually is the planet that we know most of. So we know that every day, 20 to 50 tons of micrometeoroids actually interact with Earth atmosphere. And the same, of course, can happen on different planets. Well, before all of this, it's interesting to see what are these sort of tiny pebbles doing in our atmosphere. So what they are actually doing here by ablating in our atmosphere, they are fragmenting, and all this sort of material actually spawns our sodium layer. And later on, actually create nucleation center, nucleation point where polar mesospheric clouds can actually be formed. So these are the one that you can see in the northern side of our world. And in general, they also influence the ozone chemistry. And even some speculate these material that actually happen to fall onto the sea actually happen to nourish the marine ecosystem. So in a way, are actually constantly interacting with our atmosphere, and it seems to have a vast importance for our planets in a way. We see, of course, similar things happening on different planets. So we see, for instance, nuclear clouds on Mars. These have been spotted by Spirit and no, sorry. This has been spotted by Curiosity in 2019, and actually are proxies for the meteor ablation in these planets. But still, we don't have a lot of data. We just picture a few of them. The one you see on the left here is just a meteor that has been spotted in 2004, but we really can't tell what's going on. There are just a few frames, and this has been spotted with some ground instrumentation. Of course, it would be great to have a fireball camera over there on Mars, but I guess the Martian over there probably already, or there is no one over there to contact to get that ready. But anyway, we know their effect on other planets. We know, of course, the presence of water might be explained by meteor interaction on Venus. So we have some sort of a presence of water-bearing molecules on Venus, and this might be linked with some sort of interaction with the meteoroids, while also we know that there are some oxygen-bearing molecules on Titan, which might be also linked to the interaction with some meteoroids. Of course, we can, there is anything living on Titan to actually produce any sort of oxygen, so gotta be meteoroid at least. But anyway, the idea here is that in order to have this sort of molecules and to sort of define in a way or how they might structure in the atmosphere, we need a model. So what most people have done so far is using the single body ablation model to actually try and see where these material might deposit. This, of course, may be related with the fugacity of the specific altitude, and this might explain the presence of these specific molecules. Though single body ablation is not the best thing to do in this case, because approximately 90% of meteors observed with high resolution video camera show some form of fragmentation. These are very faint in general. The very small one happen to fragment most often than not. And so in a way, this is quite important to consider. Though I can see why people just consider use single body ablation. Very easy to use, very simple, but in a fashion probably to understand where these material might deposit might not be the best possible thing to do. We don't have any sort of these sort of camera on any of these planets, though we have a lot of them in on Earth, like the CAMO, Canadian Automated Meteor Observatory, and the EMCCD that we have on Tavistock and Elginfield that capture daily faint sporadic meteor source. And in general, what we want to do here is basically try to get all these sort of meteors, replicate them, trying to fit the parameter space, and then get the CAMO data, the erosion fragmentation parameter range, and create a Monte Carlo model in order to randomly generate sporadic sources that can be later tested. So ideally, by just create a random group of ensemble of meteors, we, after based on ocean of possibility, will definitely at some point find some that might be actually be real. And we'll test our results based on the height distribution and bright distribution of EMCCD camera that are daily recording these sort of things. I'm currently working on some principal components analysis. It's something that I discuss further on the statistical derivation of physical properties of meteor shower, which is a presentation that I gave on ACM 2023. And this is what I'm going to use to actually create some sort of automatic way to define these sort of ranges. So in case you are more interested in that, you can have a look at that link. But overall, what we want to do here is then, with this Monte Carlo model, apply it to different planets in order to have the first empirically informed fragmentation model and a base for future mission instrumentation. So that's my email. And in case you're interested, just drop me an email if you're on here from YouTube, or if you're here in presence, just ask me anything here online.